Better? Yeah. Okay, so let me give some motivations to start. So if you take anti de Sitter, here you can take some limits and connect to different type of spacetimes. For instance, if you take the flat limit from ADS, you can go to Minkowski. If you take the Penrose limit, you can get to PP wave. Or you can take a non-relativistic limits and get to those degenerate spacetimes with the two different type of metrics, Newton-Cartan ADS. Or there is also the opposite. So instead of C to infinity, C to 0, and you have the Carroll limit and get a Carrollian ADS. So the message is that from ADS, you can take limits and get to different type of spacetimes. So the question that I'm asking, working? Sorry, I think.
No, you need to click with them.
Why is it not? Okay, now it works. Yeah, so the question that I'm asking is, since ADS is related by limits to those different spacetimes, it's very natural to ask, is holography in all of those different spacetimes implied by the ADS-FT? So as we will see in this talk, it's not super clear. It's not a straightforward yes or no. And actually, there is also another subsequent question you can ask. Since ADS-FT typically has an integrable structure, a natural question you can ask is what happens to integrability when you take those limits? And how does it realize in the limiting theory? So in this talk, I will focus in particular on this non-relativistic limit. And mostly what I will say is based on this recent review of mine with my collaborator Nieto Garcia, an introduction to string Newton-Cartan holography and integrability, which, by the way, I added on the list that Jelle wrote before. So let me first give you some introductory material. Maldacena ADS-CFT. So the Maldacena ADS-CFT is based on some brain construction, which will be useful later. So the idea is that you take type 2B string theory in flat space-time. You add a stack of n d3 brains. Here you can have open strings that stretch between the brains, or you can have also closed strings. So this system you can analyze from two different regimes. One that is the strong coupling regime. In this case, the system is dominated by closed strings that they probe a black d3 brane geometry. On the other one, on the weak coupling regime, the system is actually well approximated by open and closed strings that they are described by the dBi action in a 10-dimensional Minkowski spacetime. So the idea is that then you can consider the low energy limit of both realizations. And here, from the strong coupling, you have that you can decouple two different regions of the spacetime. One that is an asymptotic flat spacetime, and the other one that is a near horizon geometry, which is described by ADS5 cross S5. On the other side of the weak coupling description, again, you have that the dBi will decouple into two different sectors, one described by supergravity in flat spacetime, and the other one that is n equal 4 super Yang-Mills in 4 dimensions. So since both the asymptotic side and the supergravity, they are the same terms that appear on both sides of this description, this is kind of the boring term, which we can forget. But then there is the other one that is the non-trivial duality, which is the duality between string in ADS5 cross S5 and n equal 4 super Yang-Mills. So the idea now is, can we incorporate limits into this picture in a consistent way, such that then we can derive a novel type of holography in this limit. So I will focus on this, the non-relativistic limit. So what we know about it, and in particular for the string theory side. For the string theory side, it has been worked out, the non-relativistic limit of string theory in ADS5 cross S5. That was done by Gomis, and Kamimura. In their procedure, that is a strict limit, they have to turn on a closed B field. So you need this critical B field in order to cancel a divergence. And what you are doing physically when you take this limit, you are zooming into a sector of your relativistic ADS5 cross S5 theory where the strings are slowly moving. So in particular, the BMN famous string of ADS5 cross S5 is not part of that sector. So the target space that the string is probing in this limit is a string Newton-Cartan geometry, and the worldsheet is still Lorentzian in this approach. And because it is Lorentzian, you can still compute the beta function. It is easy to do, well, easy. It is possible to do it in that case. And it has been shown that the beta function vanishes, and so this non-relativistic string action is actually a well-defined action for quantization, is free of Weyl anomalies. Okay, so this is kind of the cartoon of what is happening. So here is the relativistic string in a relativistic target space. After taking this non-relativistic limit, the string is so the geometry actually breaks into two different type of vielbein, which are both degenerate. One is the longitudinal tau that aligns with the worldsheet of the string, and there is some condition that impose such a property. And the other one is actually the transverse vielbein that I call E here. So basically the space-time gets a foliation of the type of codimension 2. Okay, so now I want to incorporate, as I said before, a limit into the brain construction of Maldacena. So we wanted to take a limit, omega to infinity, where omega for me at the moment is just a whatever parameter. I'm not specifying what parameter it is. It could be a speed of light, it could be a length of your system, like it could be the radius of ADS, could be an angular momentum. So I want to be generic. And I just want to set some axioms that I wanted to satisfy in order to reach a well-defined limit of the ADS-CFT. So what I find sensible to propose is that we have that the D-free brain, after taking this limit, still retains an horizon structure. So you have an horizon and an asymptotic region. Then I find sensible to propose that there is a uniqueness condition. So basically, if you take the low energy limit alpha prime and then the limit omega to infinity, those two limits commute and they give you a unique final theory. Then a holographic condition. So basically, the gauge theory is formulated on the conformal boundary of this gravity theory. There is a symmetry matching, so the symmetries, the space-time symmetries of the gauge theory, they are realized as global symmetries on your bulk theory when you evaluate them at the boundary. And then there should be a quantitative test. Basically, you have a dictionary between observables of the two theories and the expectation values of those observables, they must match. So if you demand in mind these kind of axioms, then that's what we constructed. So the first line is actually the usual Maldacena holography. So from the stack of D-free brain in the low energy, you get strings in ADS5 cross S5, and which is, on the other side, you have the DBI that gives you the n equal 4. But then, as I said before, there is this Gomis-Kamimura limit for strings in ADS5 cross S5 that gives you strings in this string Newton-Cartan version of ADS5 cross S5. The longitudinal matrix tau turns out to be an ADS2, and the transverse is basically flat space-time up to a conformal factor. So that's in my cartoon here. This is just ADS2, and here is basically flat up to a conformal factor. Okay, so basically that's the limit, and then we decided, the question was how can we fill the other boxes in this duality? Of course, making that the axioms are satisfied. So here we found that here you should have a stack of non-relativistic D-free brains that they retain an horizon, and to get such a metric, you have to do a trick where you rescale one parameter of this solution, which is actually implying that the number of brains is infinite if you want to retain the horizon. Here you have a non-relativistic DBI on this string Newton-Cartan version of Minkowski, which in the low energy limit will give you a Galilean Yang-Mills in a 3+1 dimension with 5 scalars. So as you know, n equal 4 super Yang-Mills has 6 scalars. One of them needs to be eaten up to generate Galilean Yang-Mills. And this proposal satisfies all the set of axioms that I gave you before. So it has an horizon, commutes, it is holographic, and there is a symmetry matching between those two proposed theories. In particular, the similar conformal Milne algebra with an infinite dimensional R symmetry, which I'm going to comment in the next slide. And regarding the quantitative test, that's still in progress, but I will give you some details of what we have so far. So regarding the symmetries, I just comment because maybe you're not used to those kind of symmetries, so I want to comment what they are. So this is a conformal Milne algebra. You have a time translation, dilatation, and special conformal transformation, H, D, and K, which they form an SL2R subalgebra, which is actually quite intuitive why you have it, because it's the isometry of the ADS2 tau metric. Then you have three-dimensional spatial rotations, and then you have, this is quite peculiar, is a Milne super translation. So you have an infinite amount of generators, which they are kind of a non-relativistic analog of the super translation of the BMS algebra. Just you have to swap time with space. And so that's quite is a very new ingredient that you don't have in the relativistic ADS-CFT. And what about the R symmetry? So that turns out to be infinite dimensional. So you have a SO5 rotation of your five scalar fields. And then you have some special rotation, which are infinite. They depend on time. And they mix the five scalars with one of the scalar of the Galilean-Yang-Mills theory. So that's the symmetry content. And now I want to move to the quantitative test. So the quantitative test that I want to talk to you about is take the most celebrated test of ADS-CFT using integrability, which is the string spectrum is equal to the scaling dimension of dual gauge invariant operators. So can we do something like that for this non-relativistic ADS-CFT? So first of all, you have to define a vacuum if you want to do this computation. And this celebrated computation was done in the BMN vacuum, but BMN is not a solution of this theory because is outside of the corner of a non-relativistic string theory. So what is the simplest solution where we can consider? One is called a static string. So it's really a string that is not moving. It's very trivial. It just sit on the longitudinal directions of the ADS2 tau metric with this form. Time is evolving, and then you must have this kind of winding that Jelle was talking before. And that is actually imposed by the fact that you have constraints on the action coming from canceling this divergent term. And all the transverse directions in this setting, they are all set to 0. So this solution has a classical dispersion relation that is classical energy equal to 0. It's too trivial for us because it means that if you want to do holography on that solution, the dual gauge invariant operator should be trivial because there is no scaling dimension. So we can forget about it. And let's go to the next one that is non-trivial. So the next non-trivial is basically a static string where you turn on one angular of angular momentum on this transverse space. So you can still keep the same longitudinal, but then you turn on this it's not really an angular momentum because of the space-time flatten out. It's more like a linear momentum, really. But I call it still J in analogy of what you do in the relativistic string. So because of that, we call it a folded BMN-like because it has the angular momentum unit. And the dispersion relation is like energy proportional to the J square. So that's good for us. And this folded BMN string is good also because is suitable for light cone gauge quantization due to this angular momentum unit. And the way that you do it is similar. You follow similar steps as in Gleb and Sergey review. And then you can do perturbation theory around this solution. So perturbation theory is in large string tension. And here it is horrible, really, because this Z that we are forced to turn on is not an isometry direction. So when you expand, the action is really messy and it has a lot of sigma terms that breaks a lot of covariance and everything. So it's really messy. However, as we showed with Marius and my collaborator Nieto Garcia, there is a field redefinition of those fluctuations such that so you have to engineer those G of sigma in a particular way. And if you do that, you can show that this quadratic action becomes the action of free fields in ADS2, and you have 3 massive and 5 massless modes here. Okay, so that was a kind of nice result at the beginning to investigate what is this quadratic action. And when we arrived at this point, we said, okay, so maybe we can recast all the horrible higher corrections demanding Lorentz covariance in this ADS2. So basically, can we rewrite everything as a contraction of metrics, ADS2 metric with embedding coordinates in a sort of similar way as you do when you expand around the Wilson loops? So that was kind of the kind of motivation behind it. So we started doing that, and we use a trick from this paper where we redefine the fluctuation with the higher terms, and the higher terms basically they do not spoil the quadratic; they can only contribute to the higher terms, and demanding covariance. What we found was that S3 actually turns out to be 0. Okay, so that was kind of surprising, but if you have a parity invariant of the theory, you might say, okay, that is kind of a allowed result. But then we went to the higher, we cranked it up to the higher order, and what we found is that even S4 is 0. So that's kind of smelling something surprising at this point. And then we went higher, S5 is 0, and surprise, surprise, S6 is also 0. So all the corrections, they actually go away. And we stopped at X6 because or at this stage, computation became horrible enough to cancel those terms. Just to give you an idea, this is just one counter term that we had to introduce to eliminate this S6 for one of those fields. So as you can see, it's already getting out of hand at this stage. But this gives some very strong hint that this theory is just free fields in ADS2. And so if we believe in that, I think that there is a very strong analogy with what you do when you do PP wave in a relativistic ADS5 cross S5. So in that case, your vacuum is a BMN. You expand the energy around the classical solution, and you have quadratic oscillators plus all the corrections. And by keeping J over T fixed, and you send J to infinity, you can kill all the corrections, and you go into the real BMN limit, and you just have the quadratic oscillators. So when you do that, the dispersion relation becomes exact, and the target space that you are probing, the string is probing, is actually a limit of the ADS5 cross S5. It's called the PP wave, and the limit in question is the Penrose limit. There is an analogy with what we are doing here. Instead of taking the BMN, now the vacuum for your relativistic ADS5 cross S5 should be the folded BMN string. Here the expansion around the classical solution, it has not been done, but if you have to say how it will look like a quadratic expansion plus a lot of corrections that are dominated by 1 over C powers. And now if you take the ratio C over T fixed and you take C to infinity, we must know because the result that I showed you in the previous slide, all those corrections, they must go away, and you just remain with the quadratic oscillators in ADS2 now. And the target space that you probe in this limit is actually the string Newton-Cartan of ADS5 cross S5, and the limit is not a Penrose, but is non-relativistic. So I just want to say that this limit, non-relativistic limit, and this vacuum is really just another good vacuum for expansion of your relativistic ADS5 cross S5 action, in the same way that you find it good expanding around the BMN. Okay, so now I want to go to the integrability of this scenario, because we saw that there is an exact spectrum, so there is a strong smell of integrability. The first step, if you want to show integrability of this non-relativistic action, is to show that there is a Lax pair. So let me just give you a very tiny review of relativistic strings in ADS5 cross S5. So here you start, you have the Polyakov action, but the Polyakov action is hard to guess what is the Lax pair from that one. So it is better to go into the coordinate-free language, which is written in this form. It's a quadratic action in the Maurer-Cartan, and that's the Metz-Seitli action. So this A just lives in G over H, and you write ADS5 cross S5 as a coset of G over H. And the Lax pair was given by Bena-Polchinski-Royban, and from that Lax pair you can construct actually a classical spectral curve. So this is all the business that we all know. Now the question is, can you do the same for the non-relativistic action? So the non-relativistic action looks like this one. You have this term that looks kind of Polyakov, but then you have this extra term that is given by Lagrange multipliers, lambdas, because as I told you before, there is this divergence that you have to kill and tame, so there is this extra term. So if you want to geometrize in terms of some coset this action, the first naive answer that you would write down is just to take an Inonu-Wigner contraction of your G and your H of your coset. But if you do that, that's too naive, is not enough to geometrize it, because here in this finite term that comes from the limit, there is also a subleading term that couples to the to the one that diverge. So it can couple and it contributes in here, and you have to introduce a generator that can geometrize such a field. So it is not enough to stop at the Inonu-Wigner. What helps us here is the Lie algebra expansion. So Lie algebra expansion is basically, I give you here a little bit of flavor. If you have some generator, you can divide into two sets, X and Y, and some of them you rescale with some power. So you kind of expand your generator with some power, using some powers of a parameter epsilon. And the other one you expand in a different power of parameter. So at the leading order, this Lie algebra expansion is actually the Inonu-Wigner contraction, a leading order. But then it generates higher corrections. So it generates the extension of your algebra. So at the end, this is nothing else than a truncated loop algebra, really, what you have. So with this tool in mind, we can now start engineering what could be the coset for capturing this action. So one possibility is that from G over H of AdS5 cross S5, you replace it by the Lie algebra expansion of G divided by the Lie algebra expansion of H. So if you will do that, you will capture the C expansion of this string action and the Lax pair, as we showed here. But with this method, there is actually a subtlety that you actually generate more degrees of freedom than what you will need. So perhaps, but here is more like a question, perhaps those extra degrees of freedom might be removed by a method that Yale did in the past, but at the moment is just a question. I don't know if that can be applied. So the second possibility is that G over H, you replace it by taking the Lie algebra expansion again of numerator and denominator, but you take your extra degrees of freedom, you take it away from the numerator, and you put it down in the denominator. So basically, you treat them as a gauge freedom rather than degrees of freedom. And that gives you the correct degrees of freedom, counting, and it is fine to do that even algebraically, because this algebra, that is with this extension, it has actually a name. It's called the string Bargman algebra. So it is fine even algebraically to do such a procedure. So with that kind of option, we came up with a non-relativistic version of the Metz cycling action. So we show that this non-relativistic action, that with the constraints and everything, can be recasted into this action that is quadratic in a J current. J is basically, you can call it generalized Maurer-Cartan one form, because it is your Maurer-Cartan plus a term that contains those constraints. And Z is your extension in the algebra. And from this language, we were able to guess what was the Lax pair. It's very close to the Bena-Polchinski-Roybal one, except that you have to replace one term with this generalized Maurer-Cartan. Okay, so that's nice. You have your Lax pair of your model. And now, a very natural next question is, can I construct a spectral curve from that? So we explored that question. And the first thing that you have to do is to consider the monodromy matrix associated with this Lax pair. And what we showed is that if you look at the eigenvalues of this Lax component that enters here, yes?
Is this a bosonic strip or?
We are all doing it bosonically. There should be a fermionic extension, but we are doing for simplicity only the bosonic first. Yeah. I'm not sure when the Lax pair, I don't know how to complete it, because method cycling, you have you can do it with a cube. Basically, you have those grading, you have a grading 4 basically current. Here, I don't know. It's good to explore, I think. There is supersymmetry because Gomis Kamimura did it with supersymmetry, but it's a bit more involved to understand it. So we decided first to do bosonic only to understand what is really happening. Yeah. Okay, so what I want to say is that the monodromy, it is a holonomy of the Lax pair, and we show that this Lax pair, it has eigenvalues which are independent of the spectral parameter. So, and we show this result, the proof is based on using two finite dimensional representations. So we didn't explore all possible representation, but in those two different representations, we got the same result. So then the question is, the corollary actually, let's say, about this result is that if you have this connection that is independent actually of the sigma, of the sigma variable, you can do this path integral integration exactly by hand, and you can show that the eigenvalues of this monodromy, they are also independent of this spectral parameter. And that's actually quite a dramatic result because it shows you that the spectral curve trivializes. So in other words, the quasi-momenta becomes trivial, independent of the spectral parameter. And this condition that the Lax pair is independent of the sigma applies to the folded BMN-like vacuum. So in that case, indeed, you have a monodromy that it has like in all the diagonal, there is no dependence on the spectral parameter. However, the spectral parameter comes up off diagonal because this monodromy is non-diagonalizable, turns out. And that's because we are dealing with a non-semi-simple algebra, and the fact that now the Cartan, they are non-diagonalizable, the Cartan generators, and so they can produce terms that are off the diagonal in terms of spectral parameter. So the kind of question that we still have, and I think this is still now an open question, is how can you define a generalized spectral curve that works for those non-semi-simple Lie algebras? And that would apply indeed for this business. Okay, so I am done with the non-relativistic part, and then now I want to give you a little bit of flavor of other type of limits of the ADS-CFT. So I can move to that part now. So in terms of other, because so far we have said, okay, you can take the non-relativistic limit of the Maldacena construction. Can you do it for other limits as well? So there was a question? No. So one limit that we investigated was the Carroll limit, and I did it with my master student last year. And I just tell you what is the proposal that we came up. We have a magnetic Carroll string that lives in a Carrollian version of ADS5 cross S5, which seems to be dual to this four-dimensional magnetic Carroll version of Yang-Mills with 6 scalars. And with this proposal, we managed to show that those conditions are satisfied. So there is an horizon for the D-free brane, for the Carrollian D-free brane metric. This result is there is a uniqueness, so the alpha prime commutes with the Carroll limits. And there is a holographic realization. So one is on the Penrose boundary of the gravity theory. What is still in progress is the symmetry matching, and for that we need to work out first what is the Carrollian type 2B supergravity. And then what is still in progress is to show that there is a quantitative test that supports this duality. Another limit of interest, which is of course a lot in vogue nowadays, is the flat space limit. And with that one, I can already stop at the first line because that one breaks the holographic realization. And just let me give you some flavors because it's very nice to see how the flat space breaks the holographic realization when you put in the Maldacena construction. So the bulk theory, ADS5 cross S5, both ADS and the sphere, they must have same radius. And that's because this is a solution of supergravity with a zero cosmological constant. So when you take the flat limit that you send the radius to infinity, ADS5 cross S5 flatten completely out. You have a 10-dimensional Minkowski spacetime. On the boundary theory, what is happening? So this limit, since the boundary theory is attached to ADS, because the sphere is not contributing to the boundary, a part of this R symmetry term, the limit will act to the 4-dimensional spacetime as a Carrollian limit there. So here you have the Maldacena ADS5 cross S5, n equals 4 super Yang-Mills. The flat limit of the bulk gives you string theory in Minkowski, but in the boundary limit, you have some gauge theory on a Carolian limit of a four-dimensional Minkowski spacetime. So what is the problem? This problem is that here you cannot establish duality anymore because it is not longer holographic. So there is a boundary mismatch. And this is because 9 is not equal to 4. 9 is the dimension of this boundary of 10-dimensional Minkowski, and 4 is the dimension of this Carolian manifold. So how can you fix these kind of things? Well, I think the problem is still very much ongoing and open, but I have to say that one proposal that we came up is a compactification scenario. So what we propose is that after taking this flat limit, when you get you flatten completely out ADS5 crosses 5, there could be an extra compactification that is still required that adjusts the dimension of the boundary and the bulk and the boundary. The boundary stays at 4-dimensional, but the bulk goes down to something that is 5-dimensional times an internal Ricci flat manifold. And this needs to be a Ricci flat because it needs to satisfy, of course, the supergravity equation of motion at zero cosmological constant. So a question that a very legitimate question you might ask is how this compactification will appear. Is there any dynamical mechanism that allows you to reach such a compactification? It would be nice if there would be kind of sort of Higgs mechanism where spontaneously it is after taking the flat limit, the system tells you that you have to land into another vacuum where the flat spacetime is actually compactified. But those are ideas. I still have no concrete proposal. And again, another idea that came up from that paper is the triality. So basically, here this box is the duality between the Carroll bulk limit. So from ADS5 crosses 5, you go to the Carroll strings in Carroll ADS5 crosses 5. Here, when you take the limit, you have a Carrollian n equal 4 super Mills in Carroll 4D Minkowski. And then, because the symmetries, we worked out the symmetries of this theory, and they turn out to contain the conformal Carroll algebra in 4 dimensions. But the conformal Carroll algebra in 4 dimensions is isomorphic to the BMS in 5. And those BMS dimension in 5, BMS symmetries in 5 dimensions, will be relevant for flat space in a 5-dimensional Minkowski. So what we propose is that if you will take the large radius limit from string theory that you get in Minkowski 10, and after compactifying that you go down to 5 Minkowski times something internal, this theory could actually be in a holographic duality with the Carrollian one that you get from this Carrollian limit of n equal 4. So, but since this Carrollian is actually proposed to be dual to a Carrollian string theory in a Carrollian bulk, there could be a triality that actually connects all of them. Okay, so I'm reaching toward the end. I just summarize what we've seen. So we presented an axiomatic method for consistently taking limits of the ADS-FT. And with that method, we focused then on the non-relativistic limit, which led us to propose a duality between the non-relativistic string theory in a string Newton-Cartan ADS5 crosses 5, those Gomis-Kamimura theory, and the Galilean Yang-Mills as a boundary theory with 5 scalars. So then we show that if you go if you expand around the folded BMN string, the theory is actually free of correction. So there is an exact result, and there is a very strong analogy with the PP wave. And the integrability does not come up to be on the standard form because we have seen that monodromy matrices comes up to be non-diagonalizable. You have to deal with a non-semi-simple Lie algebra, and the spectral curve is indeed still an open question. So other more open question you can ask is, okay, so we have the folded, we looked at the folded BMN vacuum for the moment. What about a more complicated vacuum? Because the non-relativistic action allows for more complicated vacuum with more spins, as we worked out here. So the question you can ask is the string spectrum around those more complicated vacuum with spins still free of corrections? Because if that turns out to be a yes to that question, then you might start wondering if this Galilean Yang-Mills with the scalars is actually a topological, or better said, a fully constrained theory. Because then it would explain why you always have this kind of sort of exact spectrum on the non-relativistic side. Another question you can ask is, does all these results that if you take this duality, where the worksheet is still relativistic because we are doing things in that sense, and if you take an additional non-relativistic limit on the worksheet, would you connect to the spin matrix theory that Jelle discussed? So I assume the answer is yes, but then you can also ask how these results interpret after taking this worksheet limit in the spin matrix duality proposed by Jelle. Another question you can ask is what about the non-relativistic Yang-Buster deformations? So that's still open. There is some computations where like the eta deformed seems to drop out the parameter when you take the limit. But maybe you can look at other type of deformation, and in those cases it's not so trivial as for the eta deformation. Then you can also wonder if you can apply other type of methods, other type of limits to this method, like the PP wave limit, the fish chain fishnet limit proposed by those people. Would be nice to see if those are consistent with all those 5 set of axioms. The p-brane non-relativistic limits. So all of them, you can get really creative and see if you have some limits that you want to check that they are consistent. And for more questions, I encourage you to take a look at our recent review, that there are much more. So thank you very much.
Thanks for the talk. A very basic question, I think. So you start with ADS 5 crosses 5, and then you do non-relativistic or Cronian limit. But so, I mean, I understand if you start with an like expansion of metric and so on already, but how, if you start with ADS 5 crosses 5, is there just one way to introduce C somewhere, or how does it work to...
So you want to do an expansion rather than a limit? That's the question, right? Instead of
no, question is more like, is there one unique way to do a non-relativistic limit of ADS 5 crosses 5, or is there several ways to introduce like this these foliations? Or...
Yeah. So that's precisely actually what Lambert and Smith they did it. Because what I discussed here is what in the literature many times is called the SNC limit, the one that basically Gomis Kamimura introduced, and that one we know that it has a nice interpretation because we have a B field that cancels the divergence, and yeah, so basically that's kind of well defined. There is a nice physical interpretation of what is happening. There is like basically a divergent energy that would appear if you take the limit from relativistically, but this B field completely clears that divergent terms, like a kind of rest mass analog. And so there is a very nice kind of near BPS bound interpretation. Now in those limits, they got a bit more exotic. They have like one that actually Smith just proved this year that it is precisely the S dual of what we did, the SNC. So that one we can say that is safer, let's say. The other one is the D3 and C limit, which has a 4-dimensional tau. And that one is actually a bit obscure how you can cancel the divergence, because the B field is actually very fine-tuned to cancel a 2 by 2 tau metric. So you can get into more exotic. There is not a unique way to say how to take limits, but then you can always wonder what is the physics and what I'm doing, and if it doesn't make sense. So
how are people searching for the generalized version of the spectral curve? As in, what are they searching for? Some sort of flag or?
Nobody's searching anything at the moment. So really, this is very, very first results, let's say. So you have to get a bit, I don't know, really, you have to relax your conditions. Because the spectral curve that I said here relativistically is trivial in the usual meaning, in the usual way of making a spectral curve as you would do in ADS 5 crosses 5. Here you have to become a bit more creative and understand really what is the conditions you have to relax to address these non-semi-simple Lie algebras. So I cannot really say anything specifically, but that's what I want to say. It's just it becomes trivial just because you are attacking the problem with the usual mind thinking. You have to change mind thinking, I think.
It's like no canonical description of the non-semi-simple case at the moment.
No. It's all unexplored territory.
Hi, thanks for the nice talk. Maybe a bit of a naive question, but then what about the field theory, right? Integrability in the field theory, I guess you probably don't have a dilation operator, so...
For the Galilean mills, right?
Yeah.
So yeah, that's has been less explored than the string theory side, and it's something that we have in progress. I don't want to commit to any concrete statement, but it could be that it could be that it is a topological theory. So it could be. I don't want to commit, but so that means that whatever operator that you find, you can only have classical scaling dimension. So you only basically sum the dimension of all your fields basically. And anything else is all trivial because maybe the theory is fully constrained. So there is no Feynman diagrams, there is, you don't have Feynman diagrams to compute corrections.
Yeah, I also have a question. So for all these cases that you studied, can you report what's the level of, because you started from integrable ADS-CFT, right?
Yeah.
So what happens to integrability as we descend, for example, in the Carroll case?
Yeah. That's a good question.
Any idea? No?
No, it hasn't been done, but it's a great question. It hasn't been done.
It's very naive, but
No,
also
it's perfect.
I try to do basic because as far as I understand, it's like this field is being developed.
Yeah.
And also another naive question is like, what happens to at what level is the testing of these dualities? I mean, at the level of so procedure of testing the spectrum, testing the correlation. Well, maybe spectrum. Any kind of kind of duality?
So now that's a good point. We are precisely at that level because we have the spectrum from the non-relativistic string theory, that is these quadratic oscillators in ADS2 and nothing else. But what is the dual scaling dimension? We are not yet there yet. But as I said, we are working, and one possibility is that this Galilean mills is actually a topological theory, is a fully constrained because we have a lot of constraints, and so there will be no Feynman diagrams that will contribute on top of the classical scaling dimension.
So maybe the analogy with PP wave actually kind of.
Exactly. Yeah.
Thanks.
Thank you.
Thanks for the talk. I think it's not really a question, but more encouragement to involve the second D in IDD. Indeed, I think these non-relativistic Yang-Baxter deformations might be interesting because they could lift the degeneracies of the spectrum and maybe lift the non-diagnosability of your problem.
Yeah. Oh, that will be wonderful to explore. Thanks for the wonderful suggestion. It would be wonderful actually to understand if there is any Yang-Baxter deformation that survives the parameter when you take this non-relativistic limit. Because with Stein we did some trial, and with the eta deformation, the parameter drops out even if you allow even if you allow the parameter to rescale with the factor of C. But so you always end up with the like the undeformed theory, really. But maybe there are other type of Yang-Baxter that they still survive, and then your question is perfectly addressable there. Yeah, thank you.
Again.